It's a huge pleasure for me to introduce our last speaker today, my colleague Fernando Collor. He's going to talk about the space of metrics of positive scalar curvature.
Thank you. First of all, I would like to congratulate Marcos for his birthday. It's a great pleasure to be here speaking, and I should also thank him for all the advice and support he has given to me ever since I came to IMPA. So we are very lucky to have him as a colleague here. So today I'm going to talk about metrics of positive scalar curvature. And so the problem I'm interested in is the following. Suppose you have a compact manifold and two different metrics of positive scalar curvature. So the question I want to address is, when can you deform one into the other without destroying the property of scalar curvature being positive? So before I get into that, maybe I will start introducing some notation. I must confess that after Paulo's talk, I feel kind of embarrassed to use the Blackboard. But someday I'll get there. Okay, so sometimes I will abbreviate positive scalar curvature by PSC. So this means positive scalar curvature. And I will denote the scalar curvature by RG, where G is a Riemannian metric. So if you have a compact manifold X, I will denote by R plus of X the space of all PSC metrics on X. So this is the space of all metrics, see, all positive scalar curvature metrics on X. So that's the space I want to study. And once I've given this definition, there are two basic questions one could ask. So the first question is this space non-empty? That's the first fundamental question one should ask. There are lots and lots of works about this. In high dimensions, there are obstructions coming from the index theory of the Dirac operator in spin geometry. Lots of conjectures. So a lot of people have worked, and they're still working on this problem. But if that space is non-empty, so we can talk about positive scalar curvature metrics on X, the second basic question one can ask is, how many connected components does it have? How many connected components? Right? So we say that if G and G prime, let's say if G and G prime are positive scalar curvature metrics, I will say that they are isotopic to each other. Isotopic to G prime, and sometimes I will use this symbol over here. If they lie in the same path connected component of such a space. So in other words, if there exists a continuous path parameterized, let's say, the interval 0, 1, inside the space of metrics of positive scalar curvature, such that G0 equals G and G1 equals G prime. So this is an isotopy kind of problem. So you can think about the second question as a question of how many non-equivalent metrics of positive scalar curvature you can put on a given compact manifold. I also, maybe it's more natural from the geometric point of view, ask this question for the moduli space. So the moduli space is just the quotient of the space of positive scalar curvature metrics by the natural action of the group of diffeomorphisms. Right, so we are identifying isometric Riemannian metrics on X. Okay, so that's the question I want to address today. And I should say that the first result of this sort is very old. It's due to Hermann Weyl. So this was done in 1916. So he answered this question for the two-sphere. So for the two-sphere, the space is connected. That's his theorem. R plus of S2, well, if you take the quotient by the group of diffeomorphisms, this space is path connected. In other words, if you start with any metric on S2 of positive scalar curvature or equivalently positive Gauss curvature, the Gauss curvature is positive, then there is a continuous deformation which does not destroy this property, and it ends with the round metric. Right? So since two given round metrics on S2 differ by a diffeomorphism, this is the same as saying that the quotient is path connected. So let me say that you can also, in this particular case, you can also take the quotient by the group of diffeomorphisms that preserve orientation, and that group is connected. So actually the full space is path connected. But if one works a little harder, you can actually prove that this moduli space is contractible. So let me give a quick proof. It's a simple proof, but not elementary, because it relies on the uniformization theorem. The idea is very simple. If you start with a metric on the sphere, suppose Gauss curvature is positive, then uniformization tells you that this metric G is conformal to a metric of constant curvature. So I can write G as exponential to F times G bar, where the curvature of this metric G bar is identically 1. So if you look at how the Gauss curvature transforms under such conformal deformations, the formula is very simple. This gives you exponential minus 2f, 1 minus Laplacian G bar of f, where f is the conformal factor. And then it's very simple to see that if you define G mu to be exponential twice 1 minus mu f G bar, where mu varies between 0 and 1. It's very simple to check that this metric has positive Gauss curvature. So the Gauss curvature of this guy can be written as exponential minus 2, 1 minus mu f. And here we can write inside as 1 minus mu times 1 minus Laplacian G bar of f plus mu. So this guy is positive because the curvature of G is positive. Mu is between 0 and 1, so this is always positive. So this is a very simple and beautiful proof of that. But of course, we're using Riemann's uniformization theorem. So then it's natural to ask what happens in higher dimensions. And of course, in higher dimensions, there's no uniformization theorem available in general, so one has to come up with other methods. And in fact, in the 70s, people realized that this is not true for higher dimensional spheres, which is kind of surprising because you would expect that scalar curvature, positive scalar curvature is a very weak condition, so you would expect that with more space, you would be able to deform it more easily. But in fact, Nigel Hitchin was the first one to, as far as I know, to realize that this is not true for higher dimensions. There are several results of this sort. Let me give you a few names. There's a result of Carr, Gromov, and Lawson. Also, there's a paper by Craig and Stolz. So the stronger result is due to Craig and Stolz. They prove that if you look at the moduli space for the sphere of dimension 4k minus 1, then this guy has infinitely many connected components. infinitely many connected components, well, for k, at least 2. So this starts at dimension 7. So there are, you can think about this, this matrix as being some kind of exotic metric, matrix of positive scalar curvature that cannot be deformed to a round metric. So this was kind of surprising. But okay, so that happens. These methods do not work in dimension 3. They use exactly this kind of obstructions coming from the Dirac operator. This is based on spin geometry. So we have this result for S2. It's natural then to ask what happens in dimension 3. But we have no uniformization theorem in general, and the problem then was that for about almost 70 years, there were no techniques to attack this problem. So the natural question is, what about dimension 3? And that sort of changed in 1982 with a famous paper by Hamilton, where he introduced the Ricci Flow. We've seen a couple of talks about that. It's just this evolution process in the space of Riemannian metrics. So he proved that given any compact Riemannian manifold, you can always start the flow. And he also proved that if you are in dimension 3, and you start with something of positive Ricci curvature, then you get a convergence result. Then he proved that rescalings g2 of t of a solution g of t actually converge to the round metric. So if you're looking at the condition of positive Ricci curvature, this is saying that the space of metrics of positive Ricci curvature, moduli spaces, is path connected. And since also the flow here, the singularity is kind of trivial, this actually says that the space is contractible as well. So that's a very nice result. And the reason the Ricci flow is a natural tool to study deformations of PSC metrics is that, of course, it preserves the condition of positive scalar curvature. So if you look at the evolution equation for the scalar curvature, RG, how it evolves with time, the equation is very simple. You get Laplacian g of t scalar curvature g of t plus twice the norm of Ricci g of t squared. And since this guy is always non-negative, follows easily from the maximum principle that if you start with something which has positive scalar curvature, then that condition is preserved with time. And that holds in any dimension. Right. If you study that a little more closely, you can bound this by, this is always greater than or equal than twice the scalar curvature squared divided by n. So if you, again, apply the maximum principle to that inequality, you actually get that the flow has to end in finite time. The scalar curvature is going to blow up eventually in finite time. So you also get this also implies that the flow becomes singular in finite time. Okay. The problem here is that, as I said in the beginning, positive scalar curvature is a very weak condition. So one can draw a picture very similar to the one coding drawing stock, sort of a dumbbell. So a picture like this. This is a metric of positive scalar curvature on the 3 sphere, and since the curvature here is very, very large, you expect this region to pinch off before the rest of the manifold. So this is a kind of singularity that does not appear if you start with positive Ricci curvature. So singularities can occur in proper subsets of the manifold, and that's a problem. Right? But again, we're all aware of the work of Perriman. He understood very well how singularities form in dimension 3. And for that, he used what is called Ricci Flow with surgery. So the Ricci Flow with surgery was actually introduced by Richard Hamilton in the context of 4 dimensions for positive isotropic curvature. But Perriman managed to understand it very well in dimension 3 and describe the singularities that conform. This comes with a description of possible singularities. I'll say a few more words about Ricci Flow with surgery later. So let me just warn you that everything I will say here relies very strongly on the work of Perriman. It's very important to know that. Okay, so yeah, so that's the Ricci Flow surgery. I will say a few more words about it later in a few minutes. Let me say that, of course, with that he proved the Poincare conjecture. It's a topological application, but he also he can also get geometric applications. For example, the Ricci Flow with surgeries in 3 dimensions actually answered the first question I put on the board if the dimension is 3. So we actually know what are the compact orientable 3 manifolds which admit metrics of positive scalar curvature. So that's follows from the work of Perriman. So let me state that as a theorem. Of course, what are the examples, right? So what are the examples of manifolds in 3 dimensions which admit metrics of positive scalar curvature? Of course, one has the 3 sphere, and we can also take quotients of it by finite groups of isometries. And we also have S2 cross S1. The product metric there is evidently of positive scalar curvature. And the other the other key condition is the key property of positive scalar curvature is that positive scalar curvature is preserved, let's say is stable under connected sums. So that's due to Romanov and Lawson. There is also related work by Shen and Yao on that. So the idea is that if you start with something of positive scalar curvature, then you have another thing over here. You can pick points. Maybe this is too far away. P and Q, right? These manifolds have positive scalar curvature, G1, G2. You can remove small balls around those points and make like little necks come out of this thing, like remove small balls and then you do something like that. And you can actually do it very, very explicitly in normal coordinates around that point. You do a calculation, you prove that you can sort of introduce this neck so that the scalar curvature is still positive, and so that near the end, the metric here is exactly cylindrical, the same over here. So since they are like perfect cylinders, you can just glue them with the cylinder here. So you get a connected sum, or say Gromov-Lawson connected sum, and this guy still has positive scalar curvature. So if G1 and G2 are PSC metrics, then you can put a PSC metric in the connected sum. The conclusion then is that connected sums of these things admit metrics of positive scalar curvature. And then Perriman proved that they are the only ones among the orientable class of manifolds. So let me state the theorem. Before, let me just remark, it's an important remark for what I'm going to do, that if you have, let's say you have G1 isotopic to G1 prime and G2 isotopic to G2 prime, then you can introduce a neck continuously along the families and prove that the connected sum of G1 and G2 is isotopic to G1 prime and G2 prime. Okay, so the Gromov-Lawson construction can be done continuously along families of Riemannian manifolds because of its explicit nature. So that's an important observation. Then the theorem of Perriman says that if M3 is orientable, compact, and admits a metric of positive scalar curvature, in other words, the space R plus of M3 is non-empty, then, in fact, this is equivalent, right? M is diffeomorphic, M3 is diffeomorphic to a connected sum of those blocks over there, of quotients and S2 cross S1. Finally, many copies of S2 cross S1, and finally, many spherical quotients. Okay, so we know all. So we answer, Perriman answered the first question I posed on the board in the case of 3 dimensions. Okay, so I'm interested in dimension 3, so those are the manifolds I want to consider. So from now on, M3 is going to be always a connected sum of this sort. So let me write it on the board. M3 is going to be something. And on purpose, let me put a factor of S3 over here, although it doesn't change the connected sum. You can have finally many of these guys, and finally many copies of S2 cross S1. So let's say this is appear L times. So M3 is going to be something of this sort. Then the theorem is that the space, the moduli space for such a manifold is path connected. So not only it holds for the 3-sphere, but it's actually true for all compact orientable free manifolds of this type. So that's the theorem I want to talk about today. There is a topological result due to Cerf in the 60s. He proved that the group of diffeomorphisms of S3, which preserve orientation, is path connected. There is a stronger result about the homotop type due to Hatcher, but that's enough for my purpose here. And that implies, because on S3, we can just take the quotient by the group of the preserves orientation. It's the same thing. So the corollary of that is that R plus of S3 is path connected. So this is the result, the analogous result of Wiles in dimension 3. Okay, let me also say that after Hamilton studied the 3-dimensional case, he also, if I'm not mistaken, 4 years later, he also studied a 2-dimensional case, 1986. He looked at the Ricci flow in 2 dimensions, and he proved that if you start with something of positive Gauss curvature, then of course the positivity of curvature is preserved, and rescalings G to the T of G of T converge to a round metric. So this actually implies Wiles' result in dimension 2, but in the end he had to use the uniformization theorem. So it's nice that a few years ago there's a note by Chen, Lu, and Tian which clarified this point, and actually you can make this proof to be independent of uniformization. So you have these 2 different proofs of Wiles' result, one which uses a very classical method, the uniformization theorem, and this other one which uses a very modern technique, the Ricci flow. And I say that because in some sense my method to prove this is going to be a combination of those two. So I use the Ricci Flow with surgeries, but I also use the conformal method. So how does one prove this thing? Of course, if you are in the three-sphere has a canonical metric, which is just the round metric, right? So if you want to prove that this thing is path-connected, you have to find some sort of canonical metric in that. The idea then would be to flow anything into that one. So let me show you what are the canonical metrics. Actually, they are not exactly canonical, but the family of them is. So let me say what a canonical metric is. Canonical metrics, because it's actually a family. You start with, so let's say M3 is this manifold, right? So what you do is, in each one of these copies, you pick a metric of constant curvature, right? So in S3 mod gamma I, you pick a metric of constant curvature. By a result of the run, they're all isometric to each other. And then what you do is you consider, let's say, the unit sphere. This is just S3 inside R4, for example. Then you pick on the three sphere, let's say, K points, P1, P2, maybe PK here. You choose a point in each one of these guys. So let me draw it like this. So you choose a P1 prime here. This is supposed to be S3 mod gamma 1. You do the same here, the same here. And then you do the Gromov-Lawson connected sum to these things over here, right? So you glue them with a small x. So there are Gromov-Lawson necks. Then you choose L pairs of points. Let's say I choose here Q1 prime, Q2 prime. Let's say QL prime. You make these little necks come out of this thing over here, like that. Gromov-Lawson necks. And then what you do is you just identify the boundary spheres with reversed orientations. So that's like adding a handle to the metric. Right? So you identify this. Sorry about my pictures, they're not very. You identify like these things. Then this gives a Riemannian metric on that manifold. Actually, this is a family of Riemannian metrics, right? But the good thing is that they are all isotopic to each other. The reason is that we can always move necks around. So if you have two canonical metrics on the same compact free manifold, you can join one to the other by just moving necks around. Right? Actually, there are several kinds of necks because the construction of Gromov also depends on some parameters. It's not a specific neck. You have actually several. You can make it thinner, right? But you can also deform them, so there's no problem here. So the important thing about this family is that they all lie in the same path-connected component of the moduli space. So if you have, let's say, G1, let me put it like this, all canonical metrics lie in the same path-connected component, the same component of the moduli space. Okay, I'm using here a topological theorem of Milner, right? The uniqueness of the connected sum decomposition. If you have two of them, then he says that there must be a orientation preserving diffeomorphism between the summands. And the theorem of Duran says that if you have an orientation preserving diffeomorphism between two spherical space forms, then you also have an isometry between those space forms. So you use this sort of stuff to conclude that. Then this strategy now I think is pretty clear. The strategy is to start with an arbitrary metric and then try to use Ricci Flow with surgery to connect it to one of these guys. So the strategy is you start with a metric in R plus of M3. Then you try to use Ricci Flow with surgery to deform continuously, right, G into a canonical metric without losing the property that the scalar curvature is positive everywhere. Okay. So let me say a few words then about the Ricci Flow with surgery. The Ricci Flow with surgery is just it's a discontinuous evolution process. It's a collection of standard Ricci flows. Maybe I should leave this thing here. So that's why I put the SC3 here, because the construction starts with a unit sphere in R4, so just to indicate that. Okay, so the Ricci Flow with surgery is a collection of standard Ricci flow. So this is a one-parameter family of Riemannian manifolds, parametrized, let's say, by the interval 0 to infinity, with some discontinuities at a discrete set of singular times. So there are some singular times ti, let's say ti plus 1. And for every one of these intervals, the manifolds we get here are our standard solution to Ricci Flow. So we actually get a collection of 3 manifolds in matrix in those intervals. So these make a standard Ricci Flow. And I also ask that this interval be the maximal interval of existence. So this solution is actually going singular at time t1, which goes singular time at ti plus 1, and such that the initial condition of the next flow, let's say mi plus 1, g I plus 1, ti plus 1. So this is here, right? So this Riemannian manifold is obtained from the preceding Ricci flow by a process called surgery. Preceding Ricci flow by surgery, which is actually done with some parameters. Right? That's roughly the idea of what the Ricci flow is. So surgery is a process that replaces a couple of appropriately chosen necks in the manifold, necks where the scalar curvature is very, very large, by something which you just cut it like along the middle, and then you replace one of the sides by some standard model here. So this is like a standard cap. So the important thing about the surgeries that Perriman were able to do is that they're all surgeries of this type. They're all on cylindrical regions and replacing one of the halves by some standard rotationally symmetric cap. The idea is then is to get rid of the regions where the curvature is very, very large. So what are the good properties that I need? Erase that. First of all, if I start with something of positive scalar curvature, then it's still all of the flows will have positive scalar curvature, and actually by the same reason I mentioned before, the flow will become extinct in finite time. That's very important. So if the scalar curvature of the first metric, which would be G0 let's say G0 of 0 is positive, then the scalar curvature of Gi of t is positive for every I in t, and at some singular time here, let's say tj plus 1, the flow becomes extinct in the sense that the manifold, the initial condition at time tj plus 1 is just the empty set. At tj plus 1, so that means that mj plus 1 is just the empty set. So what that means is that just before we arrive at time tj plus 1, the curvature is uniformly large, and then when you do surgery, basically you discard everything, you just get the empty set. So Perriman gave an argument. Okay, so let me say that this actually is kind of easy to prove if you assume positive scalar curvature, right? But it actually holds for an arbitrary metric on one of these manifolds. There is an argument of Perriman and a different argument due to Coda and mini-cosi using minimal surfaces, the finite time extinction result, which is actually very important for the Poincare conjecture. Because the idea is that if you know that the flow becomes extincted, so if you know how it ends, and if you know how it changes, then you can reason backwards and you know how you start, right? So you can prove topological results, and also that's the idea of my construction too. You can prove disconnectedness theorems. Okay, but then we have two problems then, two difficulties to address. The first one, or maybe I should say the other key property, the existence of canonical neighborhoods. There are also some special properties about related to volume, but I don't need those for my construction, so I will just mention the existence of canonical neighborhoods. So there is like a parameter, Ri. It's a very small positive number, such that whenever the scalar curvature of some point in time is greater than Ri to the minus 2, so this is very, very big, you know that X is in some canonical neighborhood. So what are those canonical neighborhoods? There are essentially three types. The first type of canonical neighborhood, so of course these manifolds could be disconnected, right? Once we do surgery, the manifold can have several pieces. So the first type is when a component develops positive sectional curvature everywhere. So that's called the canonical neighborhood. So if the whole component of X has positive sectional curvature. Well, if that happens, then we can just recall Hamilton's result. Positive sectional curvature implies positive Ricci curvature. So then you know that the metric is going to disappear in finite time and become asymptotically round. So we know what happens if these things come up. And then we have the second type of canonical neighborhoods called epsilon Eck. This is just a very small region in the manifold, such that if you scale it so that the scalar curvature becomes 1, let's say at the center, then the resulting manifold will be very, very close to a cylinder of length, which goes from minus 1 over epsilon to 1 over epsilon. So it's almost cylindrical at the right scale. And the third type of canonical neighborhood is called epsilon cap, or C epsilon caps. So those are open sets which look like this. They're also very small. And the neighborhood of near the boundary they contain, so this is a cap, but near the boundary they contain an epsilon Eck as well. And they could be diffeomorphic to, there are only two topological types. They could be diffeomorphic to a 3-ball or to RP3 minus a 3 ball, right? Okay, the problem is that for the Poincare conjecture, you actually, the topological information is enough, right? But for my result, I need to know a little more about the geometry of these things. And this is not explicitly stated in Perriman. I think in the work of Kleiner and Lotter, they are sort of there. But it actually follows from Perriman's things that these caps can be of 3 types. So type A, they just have positive sectional curvature. Okay. Type B, they're very, very close, let's say epsilon close to the standard cap. So I did not define it explicitly, but this is a rotationally symmetric manifold of positive, of non-negative sectional curvature that you use when you do surgery to replace the bad regions. So this is completely standard, rotationally symmetric. And the third type, when the topology is RP3 minus B3, then you could, of course, have positive sectional curvature, but it could be also epsilon close to the following cap, epsilon close to. It's also a standard cap. You get it by looking at S2 cross R, right? So this is a solution. If you contract the sphere, this is a solution to Ricci Flow. And then you identify antipodal points on the boundary here. So the topology you get is RP3 minus B3. So that would be it's supposed to be small, right? But this is a kind of standard cap. And the good thing about this two, the types B and C is that they are locally conformally flat. So they're like rotationally symmetric. So that's a very good property. Okay. So those are the canonical neighborhoods. So the idea is that whenever the scalar curvature is sufficiently large, you know essentially what the geometry locally is. Right? That's very important for my result. The proof then is by, let me also mention another important thing, the following property that if you pick, let's say, finitely many canonical metrics, components like the one I drew a few minutes ago, and then you join them by several necks using the Romanov-Lawson connected sum, then this whole configuration is isotopic to a single component with a canonical metric. So the connected sums of canonical metrics are isotopic to a single canonical metric. So let me explain quickly why is this true. So we have like 2 pictures like that, right? So we have like a unit sphere here also. Another one, maybe we have some necks identified over here. Maybe we have some spherical space form here. So here maybe we have 2 of them. And suppose that you connect these 2 pictures by just one neck, just one Romanov-Lawson neck, then I'm claiming that this can be deformed to a single canonical metric. And the reason is the following, because if you forget about the necks, the picture you get is the following. So if you just draw the 2 spheres connected by Romanov-Lawson neck, then since the construction is very explicit here, when you look at the spherical metric in normal coordinates, then you see that it's rotationally symmetric, right? So this picture will have this rotational symmetry, which makes it locally conformally flat. And for locally conformally flat metrics, there is a uniformization result. Every locally conformally flat metric on a sphere and also on spherical quotients is conformal to a round metric. So you can use the conformal method to deform this picture into a single round sphere. Right? So now you can remember that you had like some necks and some spherical space forms, and what you do is you just bring the necks and the spherical space forms along your path. Right? So that gives you a round sphere with some necks and some spherical space forms. So this proves this result for just one neck, but you can have many more components and many more necks, but you just do induction on the number of necks, and the result follows. So this is important because my proof is, like in the Poincare conjecture, is also based on induction. So let me say then what's the strategy, and maybe prove one of the steps of the induction process. So as in the Poincare conjecture, the proof is by backwards induction. So the idea is that, let's say that AI is the assertion that every component of MI is isotopic to a canonical metric. That's my assertion AI. Then what I want to prove is that AI implies AI plus 1, and the flow becomes extinct at time tj plus 1, right? So I have to prove that at time tj, the assertion is true, that aj holds. So if I can prove that, my conclusion will be that A0 holds, but A0 holds is just the assertion that your initial manifold can be deformed to a canonical metric. So a couple of, maybe 2 weeks. Sorry? No, it's this way, because, so we have like, yeah, you're right. Right, AI plus 1 implies AI. It's going backwards. Right, you have Ti plus 1. Here we have Tj. Tj plus 1, you get the empty set. Then you start here, right? And then you go backwards. So maybe 2 weeks ago in the Brazilian colloquium, I gave a similar talk, and I explained how you do this step. Maybe for a change, I should explain how you do the AJ holds. Let me just give you an idea of what the technique is. Okay, so what happens? What happens to the manifolds just before they disappear, right? So surgery is devised to get rid of the regions where scalar curvature is large. So if the manifold became empty at time tj plus 1, this means that just a little before, the scalar curvature was uniformly large. So if it is uniformly large, then we know that every point is contained in a canonical neighborhood. So they are unions of canonical neighborhoods. Right? So I know that at time, so M, every component, right, of, let's say, M, pretty like this, Tj plus 1 minus delta, where delta is very small, is a union of canonical neighborhoods. So then the idea is that, of course, some of them will have positive sectional curvature, but then the whole component has this property, and we just use Hamilton's result. And the other ones will be unions of necks and caps. That's the only possibility. Right? So what can happen? Suppose that you see like a little small epsilon neck. This is almost cylindrical at the right scale. So you can look at what happens at the, let's say this, the boundary here. You can see maybe another epsilon neck. You can do the same here. So if you think about it a little bit, only two things could happen, right? So this neck could maybe get around and intersect the left-hand half of this neck again. So if that happens, the manifold is diffeomorphic to S2 cross S1, right? When maybe this goes around and So if this happens, the manifold is diffeomorphic to S2 cross S1. And the other thing that could happen is that you find a cap. So here's a cap. If you find a cap over here, then when you go to the left, you have to find a cap too, because you cannot intersect back again, right? This is a manifold, so you find a cap over here too. But since the caps could be either balls or RP3s minus a ball, you get, so the list of topological possibilities is very restricted. So topologically, the only manifolds you see here are S2 cross S1, S3, RP3, and maybe RP3 connected some with RP3. Right? Maybe you find two caps of the RP3 type. So those are the only possibilities right before the flow ends. Right? So let me just say, for example, what's the argument in the case of S3, right? Then you have to remember that the caps could be of three types. If it's S3, then they could just be of the two first types. They either have positive sectional curvature, or they are very close to a rotationally symmetric cap. So there are essentially, you have to consider a couple of cases, right? So if, for instance, if the two caps over here are caps of type B, right? In other words, they are epsilon close to standard caps, then you can sort of, these necks are given by diffeomorphism. So the idea is that when they intersect each other, the product structures almost align. So you can sort of interpolate these diffeomorphisms, and since the metric is almost cylindrical at the right scale, has positive scalar curvature bounded below, right? So you can just make a small deformation at each one of these intersections to turn it into a rotationally symmetric thing. So you do like by hand. Since these guys are also almost rotationally symmetric, you just deform this thing to something which it is supposed to be rotationally symmetric. Okay? Rotationally symmetric. But then again, this is locally conformally flat, and you can use the conformal method uniformization. Use the conformal method. This deforms to around S3. So what happens if we have a cap of type A of positive sectional curvature? This is another possibility. So we might have, let's see, the same kind of picture. The only difference is now, let's say this is a cap of type B, but this is a cap of type A. So here we have positive sectional curvature. So what I do is I do an extra surgery over here. So I cut this cap comes with a little neck, right? So I do an extra surgery. And then what I do is that now I glue standard caps to both sides of it. So in the Ricci Flow with surgery, you never glue caps to both sides. It's always to one of them. But here, I can do it on both sides, right? So I get the picture like this. So now, the important property here is that surgery preserves positive sectional curvature. So if the neck you started with has positive sectional curvature, then when you do surgery and glue a standard cap, you can do it in such a way that what you have left still has positive sectional curvature. So this guy over here is going to have positive sectional curvature. And this guy here is a cap of type B, right? Almost rotationally symmetric. So then I know that this guy deforms to a round metric by the previous reasoning. And now I can use Hamilton's result and prove that this guy is isotopic to a round metric. Okay. But then I have to say something about the original thing. So then the observation is that, I'm just finishing. The observation is that if you start with a neck, you do surgery, you glue caps to both sides, and then you reconnect them with the Gromov-Lawson construction, then the key observation is that the manifold over here is isotopic to the original one. So I can deform this picture into that without changing the metric near the ends. So the Gromov-Lawson connected sum construction sort of reverts surgery. Then what I have to do is now I have to just reconnect them together with the Gromov-Lawson neck. Right? And now I know that this picture is, this manifold here is isotopic to this one over here, down there. But this is a Gromov-Lawson of two components which both can be deformed to a round metric. So since I can bring the necks along the deformations, this manifold over here is going to be isotopic to connected sum of two round spheres. And of course, this is again rotationally symmetric, so this deforms to round. So you can do similar arguments if you have two caps of type A, and if you have caps like RP3 minus B3, because the standard cap there is also has this rotational rotational symmetry. And if you have like a component of type S2 cross S1, then I'm just showing this because you can see how these canonical metrics appear if you have something like this, right? Which is just a union of a lot of epsilon x. You just pick one of these necks. Let's say I pick one here, and I do surgery over here, right? So I do surgery, and then I glue caps to both sides. I get a picture like this. And this thing now is still a union of canonical neighborhoods. But now the topology is the topology of S3. So I can use the fact that I already proved it for S3, and I know that since this is an S3 and this is a union of canonical neighborhoods, this thing is isotopic to a round sphere. But then you make the same observation, right? You can connect them together, reconnect them together by a Gromov-Lawson connected Gromov-Lawson neck. You just observe that this is isotopic to that because of that observation over here. Right. But now this is a Gromov-Lawson, this is like a handle attached to something which is isotopic to a round sphere. So if you just bring this little neck along the deformation, the picture that you get in the end is exactly a round sphere with two little necks identified. So that's a canonical metric. So that's the idea of proving the AJ plus 1, right? So the idea for proving that AI implies AI plus 1 implies AI, just quickly, is just to show that every component of MI is isotopic to a connected sum of components of MI plus 1 and components which are unions of canonical neighborhoods. The idea is that when you do surgery, you get these two regions, right? You get the region that's going to continue under the flow, which are the components of MI plus 1, and you get these regions which are just discarded. But these regions which are discarded are unions of canonical neighborhoods because the scalar curvature is large. So now, because of this step AJ plus what I just explained here, I know that these components can be deformed to canonical metrics. And by the induction hypothesis, I also know that the components of MI plus 1 can be deformed to canonical metrics. So in the end, I can deform the components of MI to a connected sum of canonical metrics, and I already said that these guys can be deformed to a single component with a canonical metric. So that's the idea of the proof. Maybe I should stop here.